When we talk about ideal gas processes, we almost always represent them with PV diagrams. And these are called PV diagrams because we have pressure, P, on the vertical axis, and we have volume, V, on the horizontal axis. And what we're going to be drawing are dots and lines. Each dot represents a state. It is one of the states that the gas was in. Each path is then the process of transforming it from one state to another. Now note that the shape and the direction of the process matters, and we'll soon be talking about why. So if you have a cycle, which is typically a closed path, you would definitely want to label each one of these dots. So just like talking about initial or final, it's important to label the dots, and if we have more than two states to talk about, you might as well use numeric labels. So in this case, we have two different processes to change the gas from state 1 to state 3. One of them changes the gas from state 1 to state 2, and then from state 2 to state 3. And note that there's kind of a complicated looking curve along the way. Then we have a process that goes straight down and then straight over. And in this case, that's actually going to be an easier process to describe, but we would break it into two parts. So again, the direction matters, so we want to draw arrows, and then the shape matters, so make sure you do that correctly. Note that we've also labeled the temperature here. That's what the 900K, 600K, 3600K means. These are temperatures. Temperatures are not directly represented on this. You have pressure and volume, that's it. But remember that our third state variable is temperature. So you want to, in general, label temperatures on here if you know what they are. And frequently you're going to be able to identify what the temperature is or calculate it based on the other information. The final thing, this has the N labeled, again enabling you to actually use the ideal gas law. So think about that. Note one other note on the units. Pascals are our typical unit for pressure, but kilopascals, so 1,000 of pascals, is going to usually be more convenient. So temperature. I've mentioned that you might want to just directly label the temperature on each point, but there is one way to think about temperatures on PV diagrams without that, which are isotherms. Isotherms are lines of constant temperature, and these are actually hyperbolic in shape. And the reason you get this, again, think about your ideal gas law, PV equals nRT. We divide V, so we have P equals nRT over V. Well, if you have constant temperature, which each of these represents, nRT is then a constant, but V is on the bottom. So if X is on the bottom and Y is what's on the left side of your equal sign, this is like Y equals constant over X. For different constants, you get different hyperbolas. So this is like a 1 over X shape. And what's helpful to know is that they're never going to intersect. That's important since you don't expect different temperatures to ever occur at the same point. That doesn't make any sense. But it's always helpful to keep in mind because that means as you move farther from your origin, you're going to have an increase in temperature. So either labeling those individual temperature points are a good idea, sometimes sketching out your isothermal lines to actually remember that can be good, and when we talk about specific processes later, isotherms become more important. So remember that areas of constant temperature are going to be lines on your PV diagram and this kind of 1 over X shape.